Hello, welcome to Circle Theorems 3. This video is going to be covering the topic of the cross ratio. So first topic, quick review. We know that if we draw two lines like this, we know that this angle here is equal to 1/2 of this arc right here. Now last time, we also extended this. If it goes to a point, then we do extend that, outside of the circle, that like, instead of here on the circle, it's out here, this angle can still be shown to be equal to 1/2 of this arc minus 1/2 of this arc. If we were to like draw this in here, the arc of these points, 1/2 of this minus 1/2 of this equals this angle. The third case we did was this one here, where it's inside the circle. So if we had something like this, and this is the angle we're trying to find, we add them. 1/2 of this angle plus 1/2 of this angle. Moving on to topic 2, we're going to be reviewing cross ratio. So for this, I'm going to draw a big circle. Up here. Like that. So now we're going to label it. So we're going to label the center. Just put a dot there. Okay. Now, here's what we are going to do. We're going to draw 2 lines on the circle. We're going to draw 2 lines across the circle, and it doesn't matter where they begin and where they start, as long as they intersect at some point. So we'll do a line like this, and a line like this. Okay? Now we're going to label these points. The center point is going to be labeled E. We're going to label this point A, point C, point D, and point B, like so. Let me slide this because I'm hitting my keyboard. So, what we are going to do, the theorem of the cross ratio theorem, the theorem states that length EA times length EB is equal to length EC times ED. Now we're going to be doing an informal proof here to just speed it up and make it a little simpler. So first, what we're going to do is we're going to draw lines. I'm going to use dash lines to show that they weren't in the original figure, between points D and B and points A and C. So, like this, and up here, like this. Now, what we know is angles CDB, this one here, and angle CAB, right here, are equal because they both intercept the same arc. Arc CB, look at this. CD, CB, A, CB. So these two have to be equal like this. So I'm going to write this down. Angle CAB equals angle CDB because they intercept the same arc. Next, we can show that angle CEA, or AEC, I'm going to use AEC here, angle AEC and angle BED. I'm going to try to get out of the way. Actually, no. I'm going to redraw the E over here. So I can put this here. These two angles are congruent because they're vertical. So angle... I'm just going to put them right next to each other for the sake of viewing. Angle AEC equals angle DEB because they are vertical. They're vertical angles, so that makes them equal. So now, this information implies that triangle EAC and triangle EDB are similar. The reasoning for that is you can prove any two triangles are similar if they have the same angle measures. Like, they all have the same angle measures. In this case, we know two of the angle measures are the same. But because the angles of a triangle have to equal 180 degrees, the values for the other angles have to be the same. So we know that these are similar triangles. And the defining quality of similar triangle is that every part of a similar triangle is proportional. So I'm going to write parts are proportional. Which means we can set up a proportion like so, that if you think about these triangles, this angle is this angle, this angle is this angle. So you basically rotate this down and this down to where point A is point D and point C is point D. You flip the entire figure and you rotate it. So that would mean that side length EA is the same as ED. So we're going to do EA over ED equals side length EC, and EC is the same as EB. Which, if we cross multiply, I'm going to push this up a little bit. If we cross multiply, that implies that EA times EB is equal to EC times ED, which is what we just proved in our theorem. So before we wrap this up, I want to do a extension of this on Pascal's theorem and an introduction to projective geometry. So what this means is, there's two examples of this. Pascal's theorem states if we take any two lines arranged like this, right? We can mark 3 points on each line that are not equally spaced, and it'll have a cool result. So let me show you. So we're going to do point A, point B, and point C, like this. And then we'll do point A, and we'll do A prime, point B prime, and point C prime. And you see, these are all differently spaced. Right? I mean, I'll move A and B. I don't have to, but it helps to show my point. So I'll move AB up here. This is A prime. So now here's what I'm going to do. I'm going to draw a line between A and B prime and B and A prime. So we'll do a line like that. And a line like that. Then we'll draw a line between C and B prime and B and C prime. It's like this. And like this. I'm going to mark these two. And then we'll draw a line between A and C prime and C and A prime. Like so. And like so. And what you'll notice is all 3 of the points are collinear. They all go on the same line. theoretically, this should work for any number of spots, but I don't know how to prove that. I suppose if we added a fourth one, we could do 8D and BD, but I haven't done that yet. Now, quick introduction to projective geometry. That states if we have a figure, or we have a plane like this. This is a plane. This is two-dimensional. And we take an object up here, and I'm just going to hand draw because I don't want to use a compass. And we have some sort of light here, which is casting light down like this. If we have, say, some lines like this, you notice these are similar lines to what we did in the cross ratio, just flipped around. What this means is that if this were to go all the way down and this were to cast a shadow, it'll create some sort of shape. It could be an ellipse, it could be an oval, something like this. But what will remain the same is the cross ratio. The cross ratio will stay exactly the same. Thank you very much for watching, and I'll see you for another video. Bye.